And I want to introduce Steve. This is a real treat. Steve is a distinguished professor here at UCSB. He's been involved in the Institute since, I think, day one, pretty much.
Getting 15.
And runs the Lighting Center, which is sort of an affiliated center of ours. And so Steve is a member of the National Academy of Engineering fellow. He's a National Academy of Inventors. He's also a fellow of the IEEE, and he's won so many awards it would take me about 15, 20 minutes to list them all. But needless to say, just to be clear, the LEDs that are in all of our houses, Steve is one of the most responsible people in the world for that body of work, and all the LEDs that now work, adding particularly the blue light, along with Shuji Nakamura, of course, so that the LEDs became a practical, usable thing. And it's really influenced the way we use lighting all over the world. But Steve is taking that work to a whole new level. He works on sort of gallium nitride efforts in lighting. He's got a whole bunch of cool applications for that in the center that he runs, Sleek here. And got his PhD from USC, and is an all-around famous guy. And he's a great speaker, so you're in for a real treat. So welcome, Steve.
Well, thanks, Mark. That was probably the most illustrious introduction I've had in a while. But anyways, really like to thank IEE under leadership of John and Mark. And in particular, been really fun working with John Bowers for over 32 years in optical materials and devices. And Umesh Mishra, Larry up here, been working with them for 32 years. So we're all going to be a little old guys. But so I thought I'd focus on not just what I do in the Lighting Center, but what we do, what we use our materials for, and the key role. So I'll talk about some of the achievements, like the LED lighting one, but I also am going to spend some time talking about future vision as well. So let's see, it was working earlier. But so basically, in IEE, we have over 15 years of achievements I'd kind of like to just highlight here, particularly the LED lighting. When 15 years ago, we were only 30 lumens per watt, which was not very efficient. It was about 10% energy efficient. And today, our best numbers are 200 lumens per watt, which is 72% energy efficient. So your normal light bulb is 5%. So you can see this is going to result in huge impact in energy savings, in efficiency savings. And just in the United States alone, in the year 2030, we will have a cumulative savings of $250 billion in electricity costs, as estimated by DOE, and verified that we're on that track. But since that initial breakthrough, we really taken the gallium nitride material system and other aspects of the 3.5s in other areas, particularly Professor Mishra, or excuse me, Dean Mishra, I should say, pioneered gallium nitride for power switching. And with Shuji, since he came here, we've now really gone beyond LEDs and now using LED laser diodes made in GaN for automotive lighting, cinema display, and as we'll see in the future, potentially even high-power lasers for laser fusion and laser dimming chemistry. And that's really part of the future vision, is we now see this material system in particular going into what's called ultra-wide bandgap power electronics. DARPA has a big new program on this in which we'll be developing aluminum nitride-based alloys, and some groups even gallium oxide-based alloys for power electronics. Your next set of glasses hopefully will have micro-LED displays in them. So you can answer your cell phone by just looking in through your glasses. And so that's some of the work we're doing when we're working with some of the media companies that sponsor our research. But we've even gone into UV wavelengths now. And during the COVID pandemic, we worked with some of our member companies to come up with UVC LEDs for sterilization of the COVID in situ for things like sterilizing your cell phone. And they even came out with an air purifier now are using UV LEDs as you circulate, and that kills all the coronavirus. So that's going to be some of the future stuff. So the Gallium Nitride Research Center here is composed of over 9 faculty members, world-leading faculty. Professor Nakamura is, of course, the most well-known for getting the Nobel Prize for his invention of the blue LED. Umesh Mishra, as I mentioned before, worked on the electronics along with Jim Speck, Claude Weisbush, and John Bowers. We work with a lot on the lasers and optics side. And Chris Vanderwall is probably the leading materials computational theorist in this area, and working with Mike Gordon and Chemi, and recent addition of Sriran Krishnamurti. So pretty big research effort here of over 40 engineers and scientists. So this is kind of what the broad scope of research applications we work on. So we're basically taking a material which is what's called a wide bandgap. It's a compound semiconductor, so it's when you combine a group 3 element with nitrogen, in this case gallium nitride or aluminum nitride, in future scandium nitride. We're coming up with new materials all the time, and that lets you make more efficient, more energy efficient devices in all these regimes. Ones you're probably not as aware of is in the power device and RF. So a lot of the 5G wireless systems now use gallium nitride as the base station amplifier. Going forward, radar systems are already being done with that. But even in the electric vehicle, Professor Mishra has been pioneering the use of power switching. So electric cars in the future, if not directly in the car, at the charging stations, will use GaN. The LED, we've expanded beyond LED lighting to, as I mentioned, UV LEDs for sterilization, and then full color, that is red, green, blue LEDs for micro LED displays. And this is going to be coming out in the next 1 to 2 years, not just for glasses, but even things like your iWatch and whatnot. My particular interest lately has been more on the laser diode realm of things, where we're working with some of the chemical engineering professors, particularly Phil Christopher, on using light to drive chemical reactions, much more energy efficient than using heat or steam reforming. In this case, we're hitting methanol, and we can generate both hydrogen and methane. We can also use the laser in the car headlight, and this is actually a commercial product now in BMW cars, where we use the laser as the headlight. We convert it into white light through a phosphor process, but that light also can be used for LiDAR, so collision avoidance, and self-driving cars. So you kind of get both a lighting aspect, but you also get the LiDAR aspect as well. And that's both on BMW and Audi high-end automobiles already. And then finally, I touched a little bit on the wavelengths for quantum computing. Need blue and green and even UV. And so that's, you'll hear the talk later from Galen Moody, and he's using some of the off-shelf lasers now, but we're working with, I think, 3 companies on those aspects. So let's talk about our, what I think is one of the biggest success stories that came at least out of our labs here, is basically what's called solid state lighting. And this is the spectrum of sunlight. And I didn't put on here what fluorescent light looks like, but fluorescent light is basically a peak here in the violet, and kind of a very blotchy peak that doesn't look like sunlight very well. So initial blue LED with a phosphor looks like this peak here. So you're missing some gaps here. So after Professor Nakamura came here in the year 2000, we developed what's called a very high efficiency white LED, in which we used multiple red, green, blue phosphors combined with ultraviolet or violet LEDs. And these LEDs are very close to replicating sunlight. And this is now a name of actually one of our companies that we work with that funds us. They make a product called Sunlike. And it's very good for the home lighting. So if you have what I call older LED lighting, you're using this technology, you might want to use some of even GE has now a full spectrum sunlight. And this is actually much healthier for your eyes and some other reasons. So this was initially described in a Nature Photonics paper, wow, over 14 years ago. Anyways, let me just show you a little bit more about this achievement in historical. So I think when the white LED really started to get commercial, it was, we'd gone to some big lighting companies, and we were sitting around here, and they said, well, we have compact fluorescent, and you guys are about the same efficiency here. It's about 50 lumens per watt. And, you know, I don't think you're going to beat linear fluorescent. It took linear fluorescent about, and I was told this directly, it took 4 decades for fluorescent lighting to beat, you know, incandescent. So they said, this is going to take you a couple decades, so come back in a decade or so. But you can see in a very short span of time, not only did LED lighting beat compact fluorescent, it beat linear fluorescent, which is the lighting we have here now is LED above the screen that John turned off. Anyways, as a manufacturing basis, we're now at 150 lumen per watt. Our best R&D result was last year. It's at 200 lumen per watt. So you can see the LED efficiency is much greater than all other forms of lighting. And that's why you're starting to see it everywhere in car headlights, rooms. And we're just trying to make that better, more healthy for you than the fluorescent lighting. And that's kind of where we're at there. This achievement got Tsuji Nakamura the Nobel Prize in 2014 because the fundamental breakthrough he made was actually in 1994, back before he came to UCSB. But what we did when he came to UCSB is we took that from 30 lumens per watt all the way up to 200 lumens per watt. The theoretical maximum, by the way, is 300. Nobody's there yet, but we'll get there. But I just wanted to point out something John said earlier about Unite to Light, this nonprofit he helped fund. They're replacing kerosene lamps. So kerosene lamp puts out 0.1 lumen of light per watt of power. So you need about 1 lumen to read at night. Yeah. So that means you need about 10 watts. That's why you need to be, kerosene lamp needs to be burning about 10 watts. So with 1 watt of LED light, we can do about 200 lumens right now. It looks this much brighter. And so it's not just that you're saving all the CO2 generating from that, but the energy consumption for lighting in the third world is literally a factor of 2,000 more. They require 2,000 times more energy to generate the same amount of light that you can get with LED lighting today. So this was the huge impact that Nobel Prize Committee looks for. So the impact has been pretty big over the last just 10 years. And this is from the Department of Energy program fact sheet. So we're right here in 2023. So we've already gotten to about 19% savings. But by 2030, in the US alone, we will have saved 46% of the electricity needed to generate lighting. And this is not worldwide numbers. This is in the US alone. It's 50 power plants of energy. So this is, I think, a tribute to IEE and John's vision for help including this effort. So thanks, John, for the initial funding here. And big impact. Unfortunately, we don't get any revenue from this or patent revenue. We do get patent revenue, but not as much as I think the university would have liked for the amount of impact. But I think we did have a big societal impact. So that's lighting, but other things you're starting, like I mentioned, basically all electric cars are using LED lighting now. There's no more halogen. There's no more, even some people are using primarily halogen, but there's no more halogen lighting in car headlights for electric vehicles, like Tesla's gone all electric. So that's another big area. Saves about 2% of the energy at night if you switch to LED lighting. And so that's why it really makes sense for electric cars. Gas cars, it also saves energy, but it's not as prevalent as the electric. But in the food energy area, LED lighting for growing plants, particularly in Carpinteria, south of here, they grow a lot of plants at night. It's all LED lighting, and they save a lot of water too, because it turns out if you grow inside one of these hot houses, they also grow tomatoes there. You do save, it only uses 2% of the water. So these indoor hothouses are tremendous. In fact, the Netherlands is the world's second leading producer of food in the world after the United States. It's almost all grown in their hothouses, and it's basically because they're so efficient, they're able to be the net exporter of food in an area that's as big as Santa Barbara County. The Netherlands is a very small country, but if you fly over the Netherlands at night, you will just see a lot of blue and red lights, because that's the only wavelengths that plants really need is blue and red. They reflect green. And so that's been a big impact as well for agriculture. Of course, most of your TVs are using either the inorganic LED lighting, or now they're using Alan Heger's invention, which is the organic LED lighting. So those are the two main display technologies. Okay, so that's the achievements and kind of the past. This is the future. I always say the future looks bright. I think Umesh said that first. The future looks bright. Anyways, we believe that this material system will be the next silicon. We can grow it directly on silicon by this is called heterogeneous integration, various ways to do it. But like I said, power switching adapters, that is the adapter here, is currently, they're sourcing gallium nitride there. We hope to eventually displace the silicon carbide in the Tesla with gallium nitride. I think that'll take a few more years, but we'll get there. But other applications I mentioned, communications and radar systems are using this material system. And then really getting high resolution displays into your glasses. This is where all the major, I'd say, media companies, Google, Meta, working with Meta on this. We're working with Google on making really displays that you can put directly in your glasses and that they're bright enough. So your next computer is not going to be your cell phone anymore. It's going to be your glasses combined with maybe a device that's in your pocket, because you can really start to do some very high resolution displays that appear 3D to you This still needs a lot of work, so it's not going to you can't buy this next year. This, I think it's still 4 to 5 years out, but it's coming. And there's some debate whether it's going to be LEDs or it could even be a laser projector there in the glasses. So that's going to be a big area. Basically using the green is a wavelength needed for quantum computing, also the blue is, and even the ultraviolet. And then Tom asked me, what's this with laser fusion? Well, it turns out the NIH needs 351 nanometer laser light. So that's something we can produce. So Suji recently started focusing a lot of effort on making direct diode 351 nanometer, because the only reason why laser fusion today isn't energy efficient enough is because the input light that's coming in is only a few % efficient. They're generating net energy gain in the reaction, but the actual power system and the light delivery. So as you all know, I think John has lasers in the infrared that are 70% efficient. If we can get lasers at this wavelength 70% efficient, then that makes laser fusion much more economically feasible. This is going to take a lot of work because they need pentawatts of power. So this will take a decade. Okay, so this is why I told Umesh to come to this talk. He really is the key pioneer. He basically said, yeah, blue light's great, but let's use it for something else. I got this, who is it at ONR that funded us for the initial reactor? No, Jerry Witt at Air Force. Yeah, Umesh convinced Jerry Witt we should take one of our reactors and convert it to gallium nitride by adding ammonia on. I think it would cost $50,000, and the guy just wrote him a check. And so I think Umesh promised him radar, actually. And so this was about 25 years ago. That was really a long shot. I'd call it a moonshot. And today, you can actually get radar systems. The Navy has them on ships now that use this material system. So it's been a huge key success for DARPA. Umesh then said, well, we could use it for power adapters. That took 2 decades, but you can now buy fast chargers. This is one from Anchor. This will charge your iPhone 4 times faster. I can't believe Apple doesn't sell this along with their iPhone yet. They don't even sell it in the store, but Samsung just announced that they will now switch to gallium nitride for the standard power adapter, because 4 times faster, your teenagers really will like that. And of course, the base stations. And going forward, 6G, it's not even just the base station anymore. It turns out all the filters now are going to aluminum scandium nitride. So we didn't think this material system would do all these things, but this is a view graph I stole from Umesh, courtesy of Transform, but he now, it's not just limited to power supplies. We think you can even do rail traction, electric ship vehicles. We're going to need some very big wafers to do these things, but it just helps the energy efficiency. So just the electronics application alone will be as big in energy efficiency savings or bigger than what it is for lighting. Because if you can switch to the cars with this, then it's all over. So these are the current energy efficient materials we're pursuing at UCSB. Umesh is primarily focused on the aluminum nitride based compounds here. Sriram, Krishnamurti, and Speck are doing gallium oxide. And all these things you can see, if you're turns out if you're down to the low to the right on this is actually the best spot to be. But you can see where silicon is. So all these materials are orders of magnitude less resistive than silicon. And so that means they don't heat up very much when you use them. So being down here low on the on resistance is good. And then being high on the breakdown voltage lets you do these really big power applications. So this is kind of the future of that material system. This is my view graph. So I've been working on micro LEDs since about 2015, but this is what I think is the next big thing. And so that is basically taking your big football stadium screens and shrinking it down really, really small and shrinking it down so it fits in your glasses. So Google has now moved very actively into this space. And I went to a concert in Las Vegas yesterday, so this is my self-picture that I want to take, because I thought this was the coolest thing. This is the world's largest LED display. It's called the Sphere, and U2 was playing a concert there. But this is during bright sunlight. This thing is so bright that there was about 500 people just sitting outside taking pictures of it, because they were making a planet, and this really looks, you have to look really close to see the LEDs, but I didn't embed the video, but this thing looked like the rings of Saturn. But so think small and think big. I think you're going to see more of these virtual theaters, because when you go to see the concert, you have the entire roof and ceiling. It's like you're really there. It's not like you're looking at a flat screen anymore. So I think the future of displays will continue to be gallium nitride for some time. So why does that take so long? Basically, this is the size of an LED used in your LED light bulb. This is the size we shrunk it down to, 20 microns, and we've now gone even to 1 by 1. So it actually takes a lot of research effort to go from this big device to this small device, both in the material science and the device design. And if you can do that, then I said that you'll get all these other things. You'll get wearables, handhelds. This is a really cool thing I saw at Society for Information Display. It's a projector that's as big as a match. And this projector is so bright, you could hold it about 10 feet from the wall, and you could project a movie from this thing. So this is not commercial yet, but maybe you don't need to wear the glasses. So some people complain they don't want to wear glasses. But one of the demos was the guy took a phone call on his hand, and it was projecting from this little teeny matchbook projector. So there's lots of innovation occurring in this space. Samsung, like I said, think small, think big. They made the largest TV in the world. This is 300 inches across. So this is a really nice, called micro LED display TV. Its resolution is about 8 times better than what you see at Costco, so it's very lifelike. However, it costs $100,000. This one here only costs about 20. So I think you'll see more of the smaller displays. And how does that play into energy efficiency? So this is where OLED is today. It's about 30 to 40% of the consumption of a LCD TV. Micro LED, by the way, the RGB models today are 90% lower energy consumption, so 1/10 the power. So then you don't have to recharge your Google Glass every hour. You can go about 10 hours. Same thing with the iWatch. You'll be able to go a couple days without having to charge your watch. So huge benefit for energy efficiency. And like I said, the LEDs are incredibly bright. So if you look at here at brightness, the sphere in Las Vegas I showed you was at about 100,000. So that's why they had to go to LED to see the sphere during daytime. Otherwise, it's not bright enough. So these are the material systems, because I'm in the materials department. Currently, micro LEDs use aluminum gallium indium phosphide for the red and indium gallium nitride for the blue and the green. We'd like to replace the red with InGaN, so that's been a big focus. However, you can see we're still at about 6% efficiency. We need to get it up above 10 to be really competitive with this material system. If we can do that, then you can use one reactor, one material system, grow all 3 colors. And then I just wanted to point out, I mentioned we are at 20 microns. One of the graduate students just graduated last month, Jordan Smith, has made a 1 micron size micro LED. And we've recently been approached by a data center company because they don't want to use this for a display, but each one of these can be modulated at a gigabit per second. So obviously, a 100 by 100 array of these things will do several terabit per second. And the advantage is the cost of this thing is literally less than $1. So it doesn't have to necessarily be lasers for some of these applications. And there's a couple companies looking at now using these arrays for communication systems. So your display may not just be to look at anymore, but you can communicate vast amounts of data by modulating these things. And he thinks I'm out of time, so the last area of interest is basically some work I'd like to acknowledge, the seed support of IEE. We just got this just a month ago, and that is to combine our technology with what Phil Christopher's doing, where we can tune the light wavelength here and basically drive chemical reactions instead of using heat. It's actually more efficient if you use light. The one we're looking at in particular is to produce green hydrogen directly from liquid ammonia on the surface of Phil Christopher's catalyst. That has the advantage that you can generate hydrogen in situ from a liquid source. And so Phil believes that chemical production using light is now getting cheap enough that the cost of the LEDs have dropped so far. And the last one is the laser fusion one. This was what NIH used, where they combined 192 laser beams at 351 nanometer to basically get inertia fusion of hydrogen to helium. I think I will end because he's telling me, but I want to end with this one. So the other aspect is that we're now making lasers in the visible to UV to the kind of the green range. And this is an important wavelengths for what's called quantum computing. So they do a lot of trapped ion computing. Depends what ion you use here. These are the ion lines here. But a lot of these wavelengths we can access with this material system. So I think the future is very bright. We have basically a real wide range of applications we're going after now with our materials, and it looks like the future is still bright. We just have more work to do. And we'll hear more on this from Galen. Thanks.
Thank you, Steve. Wow, that is so cool. That's like, I mean, what applications can you not apply this to? That's amazing. It's incredible stuff. Gail, why don't you come on up? So one quick question for Steve while Galen's setting up. Yeah.
So DOE did that study because they were concerned, like with solar power, it takes a couple of years to recover those costs. With the LED lighting, because of the size of the chip, is about 1/1000th out of a solar cell. So it was a 6-month payback period to get all the costs, because gallium is a byproduct of aluminum lining anyway.
Right, but that generates profit.
Yeah.
Is that factored in?
Yeah, it's factored in. All that's recovered in the first 6 months of running your LED lighting. But yeah, that was a question early on, like 15 years ago, and then DOE spent some time and money going after that.
Okay, thanks again. Let's thank Steve again.